So you've probably heard that Node.js is fantastic for building fast, scalable network applications, handling lots of connections or, heavy I/O stuff without breaking a sweat,
Right.
which is fascinating, right? Because your actual JavaScript code, well, it's running on a single core, just one thread. How does it possibly manage all that concurrent work without constantly getting stuck?
Yeah, that's the magic trick, isn't it? That capability, it really comes down to a core concept, the Node.js event loop.
The event loop app.
It's like the engine room, the conductor, making sure everything happens smoothly, asynchronously. It's what allows Node.js to be non-blocking, even with that single JavaScript thread.
Okay, so it's not like it's spinning up tons of threads for every user or request.
Yeah.
It's more about being really, really smart with that one thread.
Exactly. Think of it like a super efficient restaurant. You've got just one waiter that's your JavaScript thread.
Okay.
Now, instead of taking an order, going to the kitchen, waiting for the food, serving it, then taking the next order, which
Oh,
would
see,
be
I
slow, right?
totally block it.
Yeah.
Yeah.
This waiter takes your order, gives it straight to the kitchen. That's like the Node.js API is handling slow stuff like reading files or network calls, and immediately moves on to the next table.
So the blocking part happens somewhere else, off the waiter's main path.
Precisely. The waiter is freed up. And the event loop, well, that's how the waiter knows when the food's ready or, when an async operation is done.
Mm.
There are a few key parts here.
Lay them out for us.
Okay, you've got the call stack. That's where your normal synchronous JavaScript code runs, line by line.
Standard stuff.
Right. Then, when that code calls something slow, like fs.readfile or a set timeout, that task gets handed off. It's offloaded to the Node.js APIs. These are built-in, often native handlers for these operations. They work outside the call stack.
The call stack doesn't get blocked. It stays free.
Exactly. It stays clear, ready for the next immediate instruction. Now, when that background task finishes, the file is read, the timer pops. The function you wanted to run after that, your callback function, it doesn't just jump back onto the call stack.
Where does it go?
It gets put into a line, basically. A queue, often called the callback queue. Sometimes you hear task queue or macro task queue.
Okay, a waiting area for finished tasks.
Yep. And this is where the event loop itself comes in. It's constantly running like a cycle. Its main job is to check, is the call stack empty?
Meaning, is the main JavaScript thread doing anything right now?
Correct. If the call stack is empty, the event loop glances over at the callback queue. If there's a finished task waiting there, a callback.
It grabs it.
It takes the first one from the queue and pushes it onto the call stack, and then the JavaScript thread executes that callback. That's the fundamental loop. Offload, queue the result, wait for stack clear, execute. And actually, it's a bit more structured. The loop goes through specific phases each turn, checking different types of queues like timers, I/O, immediates, in a set order.
Okay, that clarifies the basic flow. Offload, queue, loop, check, stack, executes. But you mentioned queues, plural, and there was something about microtasks and macrotasks. That seems important for, the exact order things run in.
Yes, this is definitely a key detail, and it's where things can get a little more nuanced, but also explains a lot. So those callbacks we just talked about from set timeout, file I/O, set immediate, those are generally considered macro tasks. They go into those queues managed by the event loops phases.
Okay, macro tasks. Got it.
But there's another higher priority type, microtasks. These primarily come from process.nextTick and promise resolutions, like the callbacks you attach with.
Higher priority. So they cut in line.
Essentially, yes, they get special treatment. Here's the rule. After a piece of synchronous JavaScript finishes running on the call stack, and before the event loop moves to the next phase or checks the main macro task queues, it first checks if there are any pending microtasks. If there are, it runs all of them. First, all the process.nextTick callbacks, then all the resolve promise callbacks. Only after that microtask queue is completely empty does it proceed to the next phase or handle the next macro task.
Wow. Okay, so even if I had a set timeout with 0 delay, its callback is ready in the timer queue, right?
Right. Yep, ready to go in the macro task queue for the timers phase.
But if, in the meantime, a promise resolved or a called process.nextTick, those callbacks will run before my set timeout 0 callback, even though the timer technically finished.
Exactly right. Process.nextTick runs first, then promises, then the event loop might get to your timer callback in the timers phase, or an I/O callback in the pull phase, or a set immediate in the check phase. The microtasks always execute immediately after the current synchronous script finishes, before anything else asynchronous.
That makes a huge difference in predicting code behavior, especially with promises chaining together.
Absolutely. Understanding that microtask priority and the general phases of the event loop for macrotasks is fundamental. It demystifies why your asynchronous code runs in a specific order, and crucially helps you write code that doesn't accidentally block that precious single JavaScript thread. Keeping it free is key to that Node.js responsiveness.
Right. It all ties back to keeping that main thread available. So thinking about this, how might understanding these distinct phases in the strict priority microtasks how might that change the way you approach writing more complex asynchronous code, especially when you really need things to happen in a specific sequence, or maybe when you're trying to handle errors across different async steps?